Okay, so we're going to be talking about probability and how we can use probability to determine different outcomes. So just a little introduction, some vocabulary. Probability itself can be defined as the chance of an event occurring. So that is the definition of probability. A probability experiment, and I'm going to abbreviate probability as PROB. A probability experiment is the chance process that leads to a well-defined result called an outcome, which gives us an outcome is the result of a single trial, meaning one, of a probability experiment. So the chances of the outcome is one time. Then we have something called the sample space. And the sample space is the set of all the possible outcomes in an experiment. So if I do something, every time I get an outcome, that is part of my sample space. And you probably have maybe heard that term from chemistry or biology or physical science. If you're doing labs, we talk about a sample space. And then the last thing is an event. The event consists of a set of outcomes of a probability experiment. So we have the probability of any event is the number of outcomes in the event over the total number. So the actual probability of something happening, our experiment, is the number of outcomes for that event over the total number in the sample space. So that's what that means. Okay? So for example, before we begin, so we have a deck of cards. So we're talking about a deck of cards. These are playing cards. And you can see them here. Sometimes they're red, sometimes they're blue. And we have 4 different types of cards or suits. There's a spade, a heart, a diamond, and a club. And for each one of these, there are numbers 1 through 10. And then we have jacks, queens, kings, and aces. So there's actually 13 of each one of these. So there's 13 diamonds, there's 13 spades, there's 13 hearts, and there's 13 clubs for a total of 52. If you ever heard someone say 52 pickup, that's what they mean. So we're talking about cards, and here you can see them all. And so there you see you have, these say T's, but these are aces. So you have 4 of each one, 4 aces, 4 twos, 4 threes, and so on. And then you have 13 in each one of these, right? So there's our deck of cards. So you get the idea. So when we're talking about this very first example, it says for a card drawn from an ordinary deck, so no tricks, no magic tricks going on, find the probability of getting a queen. Well, there are 4 queens in a deck. There's the Queen of Hearts, the Queen of Diamonds, the Queen of Spades, and the Queen of Clubs. So there's 4 queens total out of the total number of cards is 52. So the probability that we pick a queen, I'm going to shorthand Q, is 4. That's the total number of queens we could get out of 52, which is the total number of cards that we have. And this will simplify to 1 over 13. So that's the chance, the probability, if I hand you a single deck and they're all shuffled up, 1 out of 13 is the probability that you will pick a queen. Okay, and then there's these other types of probability, and it's called a probability tree that we can make. So we have a family and they have 3 children. It says find the probability that all the children are girls. Well, we know that the first time for the first child, there are two chances, right? A boy or a girl, right? And then they have their second child. And well, say you have a boy first. That means that the second time could either be a boy or a girl again. Or if they had a girl first time, you could have a boy and a girl again. Then there's the third child. Well, say you had a boy first, then a boy second, then the third time you could have a boy or a girl. Then say maybe you had a boy, then a girl, then the chances for the third child would be a boy or a girl again. Alright, so there's the option that we had a girl first, then a boy, then the third chance would be boy, then a girl. Then say you had a girl the first time, a girl the second time, then the third time you saw the same probability, a boy or a girl. So then we get these different sample spaces. So we're going to go in order along things. So we can have a boy first, a boy second, and then a boy third. So we would just write that as B, B, B in a row. Then the next chance, well, boy, then boy again, but this time, girl. Boy, boy, girl. Okay, so then say boy, but this time, girl, and then a boy. So we write boy, girl, boy. And this works for anything like this. So we have boy, girl, girl. Right? So that's all the options, the different orders I could have in that first set. Now I'm going to do the same thing with the second set. I could have girl, boy, boy, girl, boy, girl, 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 boy, or girl, girl, girl. So these are all the different combinations that we could have. So how many total possibilities are there? We have 1, 2, 3, 4, 5, 6, 7, 8. So we have 8 total outcomes. This is our sample space. We have 8 different combinations. How many of these combinations has all girls? Well, the only one that has all girls, meaning it has 3 G's in a row, would be this one down here at the bottom. So we have one chance of getting 3 girls in a row out of a total number of outcomes. So the probability here of all G's is equal to 1 out of 8. Well, at any time we have to do something, especially in math, there's a couple of rules that you have to have. And the biggest rule here is that probability of any event is a number. If it's only numbers between certain numbers. So we're talking about probability. Numbers are going to be between, it's always going to be between 0 and 1. So you can have a probability be 0 and you can have a probability be 1. And what that means that is if something cannot occur, it can never happen, then the probability is, so it cannot happen, it's impossible, then that probability is 0. It has a 0 chance. If there's a probability that it's certain, meaning it will always happen, then that probability is 1. So this is meaning 0% chance and a 100% chance. So 1 is equivalent to 100%. So think about percentages and points. The sum of all the probabilities of all the outcomes in the sample space is always 1. Okay? So let's talk about a die. So a die is something you roll and it has 6 sides, right? So here we have 1, 2, 3, 4, 5, 6. Those are the sides of a die. So it says when a single-sided die is rolled, find the probability of getting a 9. Well, looking down here, is there ever going to be a chance that if I roll a die, it will land on the number 9? Just one dice. Not two, just one. Will I ever get a 9? Hopefully you're saying, no, I'm never going to get a 9. Because my only options are 1, 2, 3, 4, 5, and 6. I'm never, ever going to get a 9. So there are no 9s here. So the probability of rolling a 9, say it's slim to none, it's never going to happen. It's 0. That's what we're talking about when it cannot happen. It's never gonna be. Okay? So then we have the same 6-sided die. Find the probability of getting a number less than 7. So we're talking about numbers less than 7. Well, that means 1, 2, 3, 4, 5, and 6. Is there any way possible that we roll the die we can land on a 1? Yep. Can we land on a 2? Yep. 3, 4, 5, 6. So no matter what I do, I'm going to land on some number that's less than 7. So the probability that I land on a number less than 7 is certain. And when it's certain, or 100% always going to happen, we say it's equal to 1. That's where we get this idea between 0 and 1. It can never be less than 0, meaning it cannot be negative, and it can never be more than 1. I can't have a 110% chance. That's not the type of probability we're talking about here. It's either between 0 or 1. It can be 0, it can be 1, it can be any number in between. It can't go over. Alright, so let's turn the page. We got a couple more things. And we're talking about unions, intersections, and complements of events. And unions of events. So we talk about the union. So this is what we're talking about right now. The union of 2 or more events or all of the outcomes for either event. And unions can be denoted with the word, so the key word here is or. And the symbol, well, it looks like a U for union. So if we have this Venn diagram, and we're talking about all the things that can happen in A, or all the things that can happen in B, we're talking about all of them together. So if I were to shade it in, I'd be shading in all of A and all of B. That's what it means. We're talking about a union together. All of it together. So let's see about this example. We have 2 events, A and B, inside of our sample space. That's S. And is drawing a diamond out of a deck of cards, and event B is drawing a 9 out of a deck. Shade the diagram and indicate the union of drawing a diamond or a 9. So we're talking about this sample space is all the cards. And specifically, we're talking about diamonds being A or 9s being B. And are there any of those that are going to overlap? And I hope you say, well, not only can I have a 9 and a diamond, I can have the 9 of diamonds. It belongs to both groups, correct? So that goes in the middle, and then we're talking about the union of them together. Then that would be the probability of picking a diamond and the probability of picking on any of the 9s. Those would be my union of events. All right, talking about the intersection now. So we talked about union, we're talking about intersection. The intersection is where two events occur at the same time, or something is a part of event A and part of event B. This part where they overlap in the middle. And one of the key words that goes with intersection is and. And we use the symbol, kind of looks like an upside down U, to denote that when you see it. So we're talking about the intersections, and we have an example here. We're going to roll a die. Remember, it's a regular die, has 6 sides, numbers 1 through 6 on it. And we're talking about rolling a number, an odd number, and rolling a number less than 5. So A says these are the odd numbers, and B are the numbers less than 5. So let's start with our numbers. Let's start with 1. 1 is a part of A, but 1 is also a part of B. So I would put 1 in the middle. Then the next number is 2. Well, 2 is not odd, so it's not going to be an A, but it is a part of B. 3. 3 is an odd number, and it's less than 5, so it has to go in the middle. And then 4. Well, 4 is not odd, but it is less than 5, so it has to be in B. And the intersection is this in the middle where they intersect at 1 and 3. It's a part of A, and it's a part of B. There's something called a complement of an event. The complement of an event is a set of outcomes in the sample space that are not included in the outcomes of event E. The complement of E is denoted by E prime. This is what it means, E prime. That means the complement. So the rule for the complement is the probability of the complement is equal to 1, that's 100% of the whole thing, minus the probability of what you were already looking for. Or you could say that the probability of what you're looking for is 1 minus the probability of the complement, right? So check this out. If those two are true, then that means that the probability of the event plus the probability of its opposite, or the prime, is equal to 1. I know. That was your mind blowing. And if we were to use a diagram to represent this, a Venn diagram, then that means the complement of A, so that's everything that is not A. That makes sense. The complement of A is everything that is not A. It's the opposite. Everything that is not A. Notice everything is shaded in except for A. That's what it means to be the complement. So let's try to put this together with some examples. So the complement event. So if we wanted to roll, what is the complement of rolling a die and getting a 4? Well, its complement would be then rolling a die and getting any number than 4. So rolling and getting, I don't know, anything but a 4, which means I can get a 1, a 2, a 3, or a 5. Oh, or 6. That would be the complement of 4. What would be the complement of selecting a letter of the alphabet and getting a vowel? Well, what's the opposite of getting a vowel? Selecting a consonant. Consonant. It would be the opposite. Okay, what's the complement of selecting a month, so months of the year, and getting a month that begins with the letter J? That means selecting a month, anything other than J. So not January, so February, March, April, May. We already have an M. June, July, can't use those. August, we already got an A. September, October, November, December. selecting a month with any one of those numbers. That would be the opposite of getting one with a J. And then the last one, selecting the complement of selecting a day of the week and getting a weekday. Well, we have two choices. We have weekdays. So what's the opposite of a weekday? A weekend. Selecting a weekend. And what 2 days are our weekends? Saturday, the best days of the week, or Sunday. So the complements are the opposite. With probability, there's also some addition and subtraction rules. And we have something that's called mutually exclusive. And things can be mutually exclusive. Basically, if they cannot occur at the same time, they have no outcomes in common. Nothing about them is going to be the same. They're totally exclusive of each other. Okay? So the example is drawing a single card and getting a 4 and a 6. So can I pick a card out of a deck and the card is a 4 and a 6 at the same time? No. I can either pick a 4 or I can pick a 6, but they cannot be the same. And because they cannot be the same, we say they have to be mutually exclusive. They cannot be the same at the same time. Okay? So how can we determine they're mutually exclusive or not? We're rolling a die. So remember our die. So we have 1, 2, 3, 4, 5. Those are ugly dies. 6. Those are the outcomes that we have. So let's see. Can I get an odd number and an even number at the same time? If I roll a 3, only one time, is this an odd number and an even number at the same time? No, so that means these are mutually exclusive. Can I get a 3? Excuse me. Can I get a 3 and get an odd number? Okay, so this time I roll a 3. There's my 3. Is this odd number and a 3 at the same time? Yes, yes it is. And because it is, then we say these are not mutually exclusive. Because they share, it can be an odd and a 3 at the same time. Alright, what about an odd number and a number less than 4? Say I rolled a 1. Is that an odd number and at the same time a number less than 4? Yes. So these are not mutually exclusive. Alright, and the last one. Can you get a number greater than 4 and a number less than 4 at the same time? So if I roll a 2, can this be a number less than 4 and at the same time a number bigger than 4? Can that ever really happen? No, and because that's a no, then we have to say that these definitely are mutually exclusive. You cannot be bigger than 4 and smaller than 4 at the same time. Okay, so the big idea here is that if things are mutually exclusive, they cannot exist at the same time. They are totally independent events of each other. They have no intersection. And that if they are, that's mutually exclusive. If they are not mutually exclusive, then that means there's some overlap, that things can exist at the same time. It has this overlap. They have an intersection. Then they are not mutually exclusive. The addition rules, we're looking for when two things could happen, where event A or, there's our keyword or, event B happen. That's our keyword. Anytime you see or, we're going to be adding. So we're saying the probability of A or B happening is whatever the probability of A is plus the probability of whatever B is. So we have an example. We have a box of donuts. And in our box of donuts, we have 3 glazed donuts. 3 glazed. We have 4 jelly. We have 5 chocolate, which gives us a total of 12 donuts. And the probability is asked to find whether we have a glazed donut, I'm just going to put G, or a chocolate donut. That means we need to find the probability of a glazed donut plus the probability of a chocolate donut. Well, how many glazed donuts do we have? We have 3 glazed donuts out of a total of 12. Or means to add. And how many chocolate? We have 5 chocolates out of a total of 12 donuts. So we add them up. They have the same denominator. 3 plus 5 is 8 over 12. And that simplifies to 2/3. So we have a 2/3 chance that we pick a glazed or a chocolate donut. Okay, now let's get into this situation's a little more on the current event side, I guess you could say. Talking about a political rally. Because we can have the probability of anything. We have 20 Republicans, 13 Democrats, and 6 independents. So we have a total of 39 different people here. If we select a person at random, we want to find the probability that this person is a Democrat or an independent. So we're looking for the probability that they're Democrat, or means to add, plus the probability that we pick a independent person. Well, how many Democrats do we have? We have 13 out of a total of how many people altogether here? 39. Or means to add, and then how many independents do we have? We have 6 out of how many total people? 39. And if we add those together, we get 19 over 39. And you can change those to decimals if you like, but you can also leave them as fractions, which I'm going to leave them as a fraction. So we have a 19 out of 39 chance, probability, of picking a Democrat or an independent. Alright, now we have the second addition rule. And this is what happens if they're not mutually exclusive. So remember, sometimes there's that intersect where an event can be part of both A and B. And there's going to be that overlap. And if that happens, and we're talking about A or B, and they can intersect, remember they're going to have that intersection where something can be a part of both, then what happens is we're still taking the probability of A plus the probability of B, but now it's being counted twice. So now something's being counted, not only is it being counted in A, it's also being counted in B. So something's being counted 2 times here. And in order to make up the difference for that, when we add them, we have to subtract the probability where they both happen. So A and B. This is the intersection part that we have to subtract away because we don't want things to get counted twice. So the first example we have here, there's a hospital. So anytime I start these problems, I always try to tally everything up and see what's going on. So in a hospital, there are 7 nurses, 6 physicians or doctors, call them physicians, 6 nurses, and 3 physicians are female. So out of that 7, 6 are female. And 3 physicians are female. If a staff person is selected, find the probability that they're a nurse or a male. Well, if 6 female, then that means there is 1 male nurse. And if 3 of the physicians are female, that means there's 4 male physicians. So here we're looking for, and there's a total of 13 staff members or people in the hospital. So we're looking for the probability that we have a nurse or a male. Okay, well, or means to add, so we have the probability that we pick a nurse plus the probability that we pick a guy, a male. But we have to take away, because there's a male nurses and male physicians. We don't want anybody to get picked twice. So we have to take away the one chance where it's both, which is the male nurse. So how many total nurses do we have? We have 7 nurses plus how many males? We have 5 total males minus how many of those males are also nurses? Minus 1 male nurse, and that's going to give us 10 out of 13. Okay, so we're going to go back to the deck of cards. I want to talk to you if you're still having some confusion about the overlap. So we have the idea, we want to randomly pick a card out of a deck. What's the probability that it'll be a diamond or a 7? So first thing I'm going to do is I'm going to circle all the diamonds. Yep. You feel me on that? I got all the diamonds circled. I have a chance of picking any of those. So there's 13 diamonds. And then I want to circle the 7s. And I have 4 7s, right? Notice that when I circle the 7s and I circle all the diamonds, I get an overlap, don't I? I have this overlap at the 7 of diamonds, so it's being counted twice. And I don't want that to happen. That's the idea here where we're having to subtract that out. See that overlap? It's being counted, not only is it being counted when I count all the 7s, it's also being counted when I count all the diamonds, and I don't want it to be counted twice because it's unfair to all the other cards. So in order to keep it fair, I have to subtract that one away. So I have to subtract that 7 of diamonds. And that's the idea here. So when I set this probability up, so there's 13 diamonds. That's a diamond. There are 4 7s. We know there's 1, right? 7 of diamonds, that extra. And there's a total of 52 cards. So when I'm looking for the probability of picking a diamond or a 7, I get the probability of a diamond plus the probability of a 7, but I have to subtract the probability of the 7 of diamonds because he's being counted twice. So we have 13 out of 52 diamonds plus 4 out of 52 7s minus that one that gets counted twice, 1 7 of diamonds. And this is going to give me 16 over 52, which simplifies to 4 over 13.